This is Chapter 5, Notes 8 on simulation. Today we're going to talk about simulations. We're going to look at independent events. We're going to describe simulations using a random digit table, and we'll actually perform some simulations as well. A simulation is actually an imitation of chance behavior based on a model. So we're going to take a look at something that may have a 50% chance of occurring. Maybe it's a weather report, 50% chance of rain. Maybe it's a player shooting free throws in a basketball game. They have a 50% chance of making it. If you're simulating 50% chance events with a coin, it's pretty easy because 50% of the time we usually expect to get heads and 50% of the time we expect to get tails. That's sort of our 50-50 chance. If you're working with a die, there are 6 sides on a 6-sided die, and maybe you say, hey, the numbers 1, 2, and 3 are going to represent half of the events, and the other half of the events are going to be represented by 4 through 6. So if I was simulating a free throw, if you roll 1, 2, or 3, that's a make. If you roll 4, 5, or 6, that's a miss. If you have a table of random digits, there are 10 possible digits to choose from. So we could pick 5 of these. Maybe the 5 smallest numbers would represent one outcome, and then the other 5 would represent another. You could also split them up into odds and evens. If you're working with playing cards, what's a way of splitting playing cards in half? Well, the cards that are black suited, that would be spades and clubs, may represent one outcome, and the cards that are red, your hearts and your diamonds, may represent the other outcome. So 50% chance, there's lots of ways that you can manipulate objects for 50% to occur. It gets a little bit more challenging when working with 75%, especially when flipping a coin. How can you simulate a 75% chance? Well, the way I look at it is you can't really do it with one coin. What you're going to have to do is you're going to have to flip a coin twice or flip 2 coins. Now, when you flip 2 coins, there are 4 possible outcomes. You can get 2 heads, 2 tails, heads and a tail, tail and a head. So based on this outcome, if I said I want something to occur 75% of the time, maybe you say, hey, 75% of the time, I get at least 1 tail. That happens 3 out of the 4 times. And then 25% of the time, no tails occur. So if you're simulating something with a 75% chance, you could simulate it using coins. Hey, there's a 75% chance of rain. Wonder what's going to happen. You could simulate it by throwing 2 coins and seeing what outcome occurs. With dice, how do you simulate 75%? Well, when you think of 75% as being like 3 out of 4, it's kind of tough when you have a 6-sided die. So one thing you could do is you could say, you know what? If you get a 1, 2, or 3, that's going to be 75% chance if we let the event of rolling a 4 be the other outcome. What about 5 and 6? Well, we're just going to say roll again if you get a 5 or a 6. That way there are really 4 possible outcomes we're going to stick with, and then you can make 3 of those 4 be the desired outcome you want. With random digits, it's kind of difficult if you're using 1-digit numbers. Now you could do the 1, 2, 3, and 4, but if you're like, I really don't want to have to skip anything, then maybe you do 2-digit random numbers. And you go, you know what, I'm going to use 1 through 75, and then 76 through 100. So you could do something like this. If you're using a random digit table, you could do 0, 0 to 74, and 75 to 99. Or if you wanted to still use these digits, you could say 1, 2, and 3 are a success, 4 is a failure. Pick a different digit if you get 0, 5, 6, 7, 8, or 9. With playing cards, what's 75% chance on playing cards? Well, there are 4 suits when you're working with playing cards, so pick 3 of them. Pick, I don't care, spades, diamonds, hearts. And then what's left over are clubs. So 3 of the suits would represent 75%. The other is 25%. So that's a way of simulating with some common objects. With simulations, we typically assume independence. And the idea of independence is the results of one trial have no influence over the next trial. So we're going to assume if we're flipping coins, if you get a head on one toss, it doesn't necessarily mean you'll get a head or a tail on the next toss. Same idea with rolling dice. We're going to assume that each outcome is independent of the previous one. So the results of one trial have no influence on what happens the next time. There's no decipherable pattern. Now we're going to simulate the likelihood of having exactly 3 girls in a family of 3 children. We'll assume a 50% chance of having a girl. If you are asked to describe the simulation using a random number table, there's a little bit of a script that's involved here when you're talking about simulation. The first step is you describe what kind of numbers from a random digit table will be assigned to each unit, in this case child. So you could say, using a random digit table, let's choose a 1-digit random number to represent each child. We're looking at something with a 50% outcome, and with 50%, that's something we can simulate with random numbers, like we set up over here. For example, 0 to 4 could represent one gender, 5 through 9 could represent the next. And that's what we do in step 2. Specify which random numbers will be assigned to each possible outcome. So we can have 0 to 4 represent one gender, we'll say girls, and 5 through 9 represents the other gender, we'll say boys. In our third step, state how many of these random numbers will be chosen or when to stop using these random numbers. If certain numbers are to be ignored if chosen, elaborate. So in this case, we're just going to choose 3 because we want 3 children in this family, 1-digit numbers. Now I suppose one thing that you could do is you could say, well, I'm going to just use the numbers 1 and 2. 1 for boy, 2 for girl. We'll ignore 3 through 8 or whatever digits you're ignoring. If you're ignoring digits, you state that here. We're using all possible digits between 0 and 9. So 0 to 4 for girls, 5 to 9 to boys. We're not skipping any, so you can just say choose 1 to 3 1-digit numbers. Then we'll state what will be counted or recorded, how many repetitions of each trial, and what will be reported at the end. So we're going to count the number of girls. We're looking for the probability of having exactly 3 girls in a family of 3 children. We'll count the number of girls. Number of repetitions is kind of up to you. This is sort of your replication task, and I think 10 usually at minimum is a good number. It doesn't state what you need to use here. I usually think 10 is a pretty good rule of thumb to work with. When you have finished, what we're going to do is we're going to report the percent of times. This will be out of 10. So we're going to report the percent of times a family has 3 girls. And we will try this out on the back side of your worksheet, which we'll go to now. So we're going to use your graphic calculator to do the simulation involving girls in a family. And unless a problem actually says to specifically use a row from the random digit table, you can use the rand_int feature on your calculator. That's fine. Now, what we're going to do is we're going to run a trial, and how it's going to look is this way. On our problem, what we're going to do is we're going to choose 3 1-digit numbers between 0 and 9. To do this on your calculator, we're going to use the rand_int feature. You can find this by going to the math button on your calculator, go across to the PRB menu, and you're going to scroll down to where it says rand_int. The first 2 numbers you type in under the rand_int are going to be the smallest and largest digits separated by a comma. So the smallest possible digit is 0. The comma is above the 7 key right here. Then we're going to do 9. And we're going to do another comma, and we're going to pick 3 numbers. And those little charts that you kind of see at the top of your paper here basically illustrate what different commands would look like if you typed them in. We're just going to use rand_int 0, 9, 3. And this generates 3 numbers. On mine, it's 828. And what we had said on the other side was that if you get a number between 0 and 4, it represents a girl. So on my first simulation, I had one number that was between 0 and 4. So I'm going to put for trial 1, I had 1 girls. If you hit enter immediately after this, it'll generate another 3 numbers. And here I have the numbers 3, 0, and 3. All 3 of these numbers are between 0 and 4. So my second trial, I had 3 girls. Now what I'd like you to do is I'd like you to try this with your own calculators. You may find you get different results than I do here. What I'd like you to do is do this basically 10 times. Count the number of girls you have, the number of numbers between 0 and 4 in each of these groupings. Write these numbers down here. When you're done, calculate the percent of trials you had 3 girls. So out of 10, and write it as a percentage, how many times did you have 3 girls? So far I have it once, but I may end up with more times. And then for right now, I'm going to put a star next to this. When I come back next week, we'll actually calculate the percent of trials that the class had 3 girls. And we'll take a look at that percentage next week when we do this in class. So go ahead, pause the video, come up with your results for these 10 trials, calculate this percentage right here. We'll do the starred one next week. So here are the results of my trials. You may obviously get different numbers than I did. Twice I ended up with 3 girls, so that would be 20%. For our last problem, W. Douglas Parker, Chief Executive at U.S. Airways, estimates that 8% of customers are no-shows for flights. So airlines will often overbook. That is, they'll sell more tickets than there actually are seats for a flight. So on a smaller 30-person flight, how likely is overbooking if 32 tickets are sold? We'll perform a simulation to estimate the solution. For step 1, describe the simulation using a random number generator. So we're working with 8% of customers are no-shows. So what we're going to do inside this box right here is we're going to fill in our script using 8% as the percentage that we're working with here. Let's see if you can fill in the correct data based on the script from the front side. I'm going to have you pause the video again, see if you can fill in the correct information inside this little box area here, and we'll take a look at your answer in just a moment. So here are basically the 4 steps of your table here. Step 1, using a random digit table, choose a 2-digit random number to represent a passenger. Why can't we use a 1-digit random number? Well, there's 10 1-digit random numbers, and there's no way that you can make 8% occur when you're using 10 numbers. You can make like 10 or 20 or 30%, but you can't make 8. So that's why I'm going with a 2-digit number. I'm going to let 00 through 07 represent no-shows and 08 to 99 be shows. If you're using a calculator, you could have said 1 to 8 represent no-shows, and then 9 through 100 represent people who show up. We're going to choose 32 2-digit numbers to represent the 32 tickets sold, and we're going to count the no-shows. We'll do 10 repetitions, which is kind of our fallback, and we'll report the number of overbooked flights, or the percent. In step 2, we're actually going to perform the simulation. The commands at the right show how to generate the 32 random numbers and sort them in an ascending list. So what we could do to generate the numbers quickly, because we've got to look at 32 at a time, is we're going to do the randint command using 00, 99, and 32. That's going to give us a list of unsorted numbers. If you actually take those numbers and put them in list 1, you could sort them numerically, and then you can see if there's any numbers that fall between 00 and 07 rather quickly. So here's what it's going to look like in your calculator. I'm going to go back to randint again, math, probability, randint, number 5. I'm going to hit enter. I'm going to type in 00, 99, 32. This will select 32 numbers between 00 and 99. If I hit the storage button, which is kind of down here on your calculator, STO, next to the on key, what it's going to do is it's actually going to take this answer, take this list, it's going to put them in list 1. If I do second and then the number 1, this actually will make list 1 on your calculator. So now I'm putting the data in list 1. And you can sort your list by going to the list menu, which is second, stat, going to ops, and choosing sort A, which stands for sort ascending. And if you hit second and 1 to choose list 1, it will sort this list for you. Now, why do we want us to sort the list? Because if you now go to your list, if you hit stat, edit, you can quickly see the numbers in order. And based on this information, I see 3 numbers in my list that are between 0 and 7. So in this particular trial, I had 3 no-shows out of 32. What you're going to do is you're going to do this same thing 9 more times and count how many no-shows, how many numbers between 0 and 7 occur. Then once you have the results for these 10 trials, to find the percent of flights that are overbooked, remember, it's overbooked if we have 31 or more people on this flight. So that means if there are 0 no-shows, that means all 32 people are showing up, or if there's 1 no-show, that means 31 people are showing up for a 30-person flight, then it's overbooked. So when you're done, count the number of times that you have either 0 or 1 no-show, and then you can use that to figure out the percent of flights that are overbooked. We'll pause the video and we'll take a look at your solution in just a moment. So my results, I had lots of no-shows. The only trial I didn't was trial 9, where I had 1 no-show. That meant 31 people showed up, so that meant 10% of my flights were overbooked. We'll calculate the class percentage next week in class.